Hello everyone, I am Prajwal Singh and I will present our work learning robust deep visual representation from EEG brain recordings. And the co-authors are Dwip Dalal, Gautam Vashishtha, Krishna Miyapuram and Shanmuganathan Raman. Now coming to the problem statement, meet Uncle Jerry. He is a chef and a secret researcher. He embarked on a journey to discover how to reconstruct images from brain signals. The brain signals we are talking about are electroencephalography signals, that is EEG, and the recorded setting is a person is shown an image. It can be of anything, and based on the response of that image, the brain signals are recorded using EEG cap that is placed over the head scalp of the person. The story started when our chef saw a pizza advertisement on the TV at night, and the next day, when he tried to bake the same pizza, at that moment, the idea of reconstructing images from brain signals struck his mind. First, we will talk about the general strategy that has been used for extracting feature extraction from the EEG signals. The work by Sampinato and Plazo et al. They train an EEG classification network. With the help of it, learn the visual representation of the EEG signals. The work by Mukherjee et al. Uses a KL divergence to learn the visual representation of the EEG signals. They used a pre-trained image classification network for feature extraction and a bidirectional LSTM network for EEG feature extraction, calculated the KL divergence between them, and using that they updated the weight of LSTM network. The work by Plazo et al. Uses a contrastive learning approach for learning EEG representation, and they trained their network in a way that it maps EEG signals to its closest positive image and far from the negative image. Following that, the work by Mishra et al. Come up, they come up with a strategy to train a variational autoencoder based method to extract the EEG features so that it can map the EEG distribution. They use a classification network to guide the complete process. Now coming to the image generation methods, Plazo et al. Proposed a conditional GAN-based method for synthesizing images from EEG features. Following this, the work by Tirupati et al. Uses a VA-based approach to synthesize images from a small EEG dataset. It also uses a supervised component, which is an image classification component. Pears et al. Modified the LSTM network, call it bio-LSTM network with attention, and uses its EEG feature along with the image feature as a condition to train a GAN for image generation. The work by Khare et al. Uses a progressive GAN to synthesize image from EEG signals. Now, coming to the proposed work, we introduce an EEG style GAN at a framework which improves image synthesizing from EEG signals by using the learned EEG representation in contrastive setting. We investigate the impact of employing a similar architecture for feature extraction across different EEG dataset. We try to see if it can perform a zero-shot classification and also a novel image-to-image translation method that we'll explain later. We further present an innovative framework for joint representation learning between EEG and images. We draw the inspiration from a clip-based method. So coming to the feature extraction strategy, we use two different architecture for the same. We use one LSTM architecture and one CNN architecture. We try to see if there is any difference in the learned feature from these two architectures. We use triplet loss for training the network. In triplet loss setting, we specifically use semi-hard triplets. Though semi-hard triplets are those which having the distance more than the positive samples but less than beta. So these are the qualitative results on different datasets. The first dataset is EEG-CFR40 dataset. As we can see, the feature extracted using LSTM and the CNN both form a very good cluster around like 40 classes. And the EEG-CFR40 dataset has around 440 time samples. Now the next dataset is an object dataset. This has 6 classes. So as we can see, the feature extraction from LSTM and CNN, and coming to the Thoughtviz dataset, which consists of 10 different classes. As we can see, LSTM feature forms a pretty good clusters in comparison to CNN. So what we observe that as the time samples, so here EEG has 440 time sample, object has around 100 or 120 time samples, and the Thoughtviz has around like 32 time samples. So as the time sample started decreasing, in case of LSTM, it forms very good, it is learning a good cluster representation. And but with the CNN, it's become dilute and dilute. These are the quantitative results for the feature representation. So our method is very close to the state of art methods. In terms of feature representation, we also perform the k-mean clustering and linear evaluation. Coming to the zero shot classification performance, for this we have used EEG-CVPR40 dataset. We train a feature extraction network on 34 classes and tested the performance on 6 unseen classes. We again use the LSTM network, and here we can see both qualitative and quantitative results. So it can, as we can see, even though the network hasn't seen this 6 classes, it forms a pretty good cluster for those all 6 unseen classes. And we can see their linear classification accuracy here. Coming to the image generation strategy, we use this style GAN architecture. We made modification to it so that we can use the EEG feature in it. So we use the pre-trained LSTM network to extract the EEG feature and then pass it to the style GAN architecture. We call it a EEG style GAN architecture. So this is the result on Thoughtviz dataset. This is result on EEG-CVPR40 dataset. As we can see, we have used the same architecture to synthesize image for both Thoughtviz and EEG-CVPR40 dataset. And these are the quantitative result. As you can see, our method is like beat a baseline with a huge margin for both EEG-CVPR40 and Thoughtviz dataset. Now coming to the other proposed work, that is image to image translation. Here what we try to achieve is we have this pre-trained EEG network, and what if we have some unseen images? We encode it to EEG feature space. These unseen images are encoded into a EEG feature space, and with this we use this pre-trained GAN, and then we concatenated the features of EEG features and try to reconstruct the image, and its equivalent EEG signals also not shown. Then it's able to reconstruct the information what this image might encode in this EEG feature space, that we can see camera and the flower and the fish. We have performed several other experiments to show the same. So here you can see the set of input image. Here you can see the set of reconstructed image, input and reconstruct. And even though the images are not shown during the training, it's able to reconstruct, it's able to get the context from the EEG data of that particular image. We inspire from the idea of clip. We train a network. We use a pre-trained ResNet 50. We train an LSTM network so that it can map the EEG features to close to the image feature. We perform several experiments that includes varying epochs and varying batch sizes. And we observe that as the batch sizes and a number of epoch increases, the representation become better and better. And we have performed the experiment on both raw dataset and filtered dataset. So the application of it, learning the joint representation, we use it. We try to see if we can do image retrieval using the EEG signals. So we use an EEG signals. You can see that the particular ground truth equivalent to that EEG signals. We extract the feature for that EEG signal, and we try to do a nearest neighbor mapping, and these are the top 5 retrieved image. Conclusion: we investigate the impact of employing similar architecture for feature extraction across all EEG dataset. We proposed a GAN synthesis pipeline that outperformed the previous SOTA FID score to showcase the adaptability of acquired representation from proposed EEG feature extraction framework. We present results involving zero shot classification performance, and novel image-to-image translation method. Our work further explored the joint representation learning switch methods, where we train a clip-based approach for EEG and image joint representation learning. Thank you.